A couple of questions have been raised recently in the practicals and on Ed discussion about parsing, what it is, how it works, especially how it was implemented in week four's practical. This recording will hopefully explain parsing, how and why recursion lends itself well to solving this problem, and hence kind of how we started to approach it in the practical. So, firstly, I want to start off with the question of what is parsing, just so we're all on the same page. Um, I like to give an example function to think about as a function you probably already used before, the parseInt function within the Java integer class. If you recall correctly, this function attempts to create an integer type from a string type. That is, we convert a string something that exists within the string class to something of the form of the integer class. So, for example, we might get an input from standard in and parse it to an integer. I want to make the distinction and note that the parseInt function doesn't actually solve anything about the number that we're putting in from the string. We're not evaluating any mathematical expression. We're not applying a plus, anything like that. We're simply changing some value from one form to another so that it's easier to perform operations on in the future. So we're just moving from different data types where, say, casting may not be possible. So in this particular practical, we looked at parsing strings that represent Boolean logic formulas into some other types. Um, we may use these types later if we wanted to make evaluation of the formulas easier in the future, because it's very difficult to, well, you can't really evaluate just within the string, so it's a lot easier to move it to a different form, and then we can use that to sort of perform operations within those classes. So tasks 0 through 3 create the classes that form the basis of how we're going to represent these formulas. So again, these classes we're creating at the start don't necessarily have to have a way to calculate or evaluate the formulas. We're simply linking back to our analogy earlier, we're simply creating the integer class, for example, and saying that we can store things in particular ways or a new way at the moment. We're not defining what plus means. We're not defining what addition means. We're not defining sort of what these operations mean. We're just sort of creating something that we're able to store the data in. So the class diagram that was provided is hopefully quite self-explanatory in nature. Um, and as a general rule, the parameters of the constructors of a class are going to be member variables within the class. And we see that this is true for most classes within this diagram. Here, the decision to all extend from a parent logic interface is made because we want to be able to perform negations or logic operations on any combinations of the other logic types. We want to be able to negate something like a symbol or another logic operation. So by implementing from a common interface, we're able to specify that sort of generic interface um, as a type, and that allows us to be more extensible in the way that we hold these classes. The choice to inherit the and or classes from the parent logic op class is also another design choice made with extensibility in mind. First, both and or will behave in similar ways and share similar features if fully implemented. In essence, there's some operation that's applied to some different sub-expressions that we're going to explore later. Um, they're only sort of differentiate by the actual expression that they are. And so with, I guess, extensibility in mind. If we wanted to be able to define other methods, this is going to reduce sort of the workload because we can just add another thing that extends from logic op, and it reduces the redundancy of code because we're not having to repeat those operations across different classes. So again, with the creation of these classes, we've only created something like the integer class. We haven't defined any way to interpret the information inside each class yet, but we're going to be able to create objects that are meaningfully identified in a way that we can represent um, the stuff from the string data and be able to store um, data in those classes in a meaningful way. So I'm going to cut to creation of the classes, and then I'll explain a couple of these classes. Okay, so bearing in mind that these classes are not going to be having any operations yet, that's why we're simply just looking at the constructors at the moment. Okay, so we're just looking for ways to store data. So the logic interface is just for purposes of being able to represent uh, all of the logic operators, symbols, and negations as a common type so that we can pass a common type into each other. So it doesn't need to have anything in it. We're not going to be implementing any specific functions across the three main types. It doesn't need to have anything in it. Logic operator, sorry. It takes in a type of a string and an array of logic expressions. And so the idea here is that there's going to be some operation, like a string that we can represent the particular operation as, and that operation is going to be applied between two or more other different logic expressions. So this will become a bit more clear when we actually start parsing the elements. But if we take AND, for example, what we find is that if we were to look at an expression, for example, if we look up here, or this OR, for example, this OR is between A and not B, okay? Or rather, A and all this, okay? Either way, we're applying the operator to some subexpression and another subexpression. And the way that we're going to store this, in this case, is in an array of the type logic. We don't know what type it's going to be yet. It's going to be either a symbol, a negate, or another logic operator. But again, we've used that logic type to be most extensible in how we apply that. A symbol is not an application between multiple things. It's just a letter in this case. So let's also be very clear that the symbol is just the letters in the logic expressions. We call the triangles and the not operators logic operators. A symbol is not an operator. A symbol is simply the letter. Okay, so the way that we can identify a particular letter, a particular symbol, can be or might be by the string representation of that symbol. And that's how we're going to store it in this constructor. And similarly, negate. So a negation is not applied between two or more subexpressions. We find that negate is applied only to one subexpression. So for example, we have negate B. Okay, the negation is only applied to the B symbol. Similarly, negate is only applied to the C symbol. If we expanded this, we might have a negation on a logic operation. Okay, if we implemented brackets in this parsing, we might be able to apply negation to a larger sub-expression. And that's why we're passing in a type logic. Okay, we want to be most extensible in what we're negating, but we don't need to have an array because we're only applying the negation to one thing at the moment. Okay, having a look at the AND and the OR classes, we've already set up the logic operator as the parent. Let's bring up the class again. So some kind of logic operator, a generic logic operator, is going to be represented by its symbol, and it's going to be applied across different sub-expressions. Okay, so we gave the example earlier, this AND is applied between the left-hand side and some right-hand side. A particular implementation of that, for example, is AND. Okay, and we use the call super to reference the constructor within logic operator, and we're going to construct a new logic operator by specifying the operator as the AND symbol, and the sub-expressions that we're going to apply the AND symbol to are going to be passed into the constructor of this function. Okay, so the AND is going to be applied across multiple sub-expressions, and where it's simply going to be the same as being a logic operator, and we're going to specify that that operator as this symbol here. Or is in a very similar fashion. We're just going to use the vertical line to represent or. Okay. So again, this is simply to describe an OR, and an AND is not necessarily to evaluate an AND. So if we were to create more functions, for example, we might have a get operator within the logic op, and that might return what kind of logic operator a particular logic operator type is, and that might enable us to evaluate an OR or evaluate an AND later. But for the moment, we're just creating these constructors and a way to store these particular objects. Okay. So hopefully that's relatively clear. Task 4, we look to actually do the parsing. So we look to write our parser. Our parser is going to take in our formula string and parse it so that it's stored as a combination of the different objects that we've just created before. Okay, so we've also been provided with a defined order to evaluate all of our logic operations. And we're going to be able to ignore all white space present within the expression as well through our implementation. So the three hints that we've been provided with are that string.trim and the string.split method may be useful, and also that this problem is recursive in nature. So if you haven't already, I would suggest having a look at the Java docs of string.split and string.trim and seeing what those methods are, considering how they may be useful in this question, and especially before we get to the end solutions, how they fit into the way of thinking before we actually get to coding this. So before we sort of hand out our code, I just want to go over understanding the recursive nature of the problem. So let's consider the following expression that we may want to pass. So we would say this as not A and B or C. So by the order of operations that's been provided, we want to evaluate the not expression first. Hence, similarly, we want to be able to be parsing it, this symbol first. So let's just put brackets around this expression here to indicate order of precedence. And I just want to be clear that the brackets here are not added to the original expression, but I'm simply using them here to indicate order of importance. Okay, so not is going to be completed first. So we'll put brackets around here to indicate this. Then we're going to want to evaluate the AND expression supplied here, and then the OR expression. So again, I'm going to put brackets around these parts of the equation, but I want to be clear these brackets here are not changing the meaning of the equation. We're simply using them to indicate the order of the precedence that we want to eventually evaluate, and hence parse these elements in. Okay, so with this in mind, we can already start to see how this problem might be recursive in nature. The reason I say this is because we have a kind of branching action down through the brackets. So if we remember back to week 1 or 2 practicals when we worked with recursion, we talked about having a base case, a recursive step, and using those to get to our final answer. Looking at the brackets, we have an eventual sort of outer case that encapsulates the whole problem. And as we go further and further down, or we might, as we call, recurse further and further down, we can become more and more specific in how we sort of apply those brackets. So as I just said, there are 2 main steps, and I'm going to add a 3rd step as well into what we need to be deciding before we look to code this problem. Firstly, we're going to need to find a base case. So a base case is going to be what is the smallest thing that we can parse by itself. What is something that we can not have other elements applied to it. It should just be itself. Secondly, we're going to have a recursive step. So the recursive step is that if we assume some part to be true, how can we use that to build something bigger? So knowing our base case, what might be the 2nd step or the 3rd step from that base case? And the 3rd step that we're going to identify is order. So now this isn't always required, but in this case it is important because we are supplied with some order of operations to apply to the question. And as we'll look to sort of explain how this works, you'll see that the order will eventually be implied in how we look to parse this through the recursive step. But I'm going to add it as a step for us to think about here. In what order sort of do we need to apply this algorithm? So firstly, a base case. We have 4 different types of strings, 4 different types of things that we need to be parsing. Of these, we have logic operators, as well as a not operator, and these are all entities applied to something else. So, for example, we have the not, which is applied to the symbol and. We have the and, as we explained earlier, being applied to these 2 sub-expressions, not and b. The 4th thing that we need to be parsing is a symbol by itself, and this is the smallest thing that exists within the formula and doesn't contain any additional information apart from that. And so for this reason, parsing a symbol by itself will be our base case. We're going to get into how we're going to identify a symbol in a second, but for now, let's just keep that our base case is going to be parsing a symbol. To solve our second step, let's look at the brackets again. The things that we have left to parse after we parse the symbols are the logic operators. Pardon me, and they are applied in this example across either one or two sub-expressions. Or we can identify this more easily by highlighting these sub-expressions. So, which is going to be applied to this symbol A. Okay. Then in blue, we have an OR symbol, and this OR symbol is going to be applied between this sub-expression and this sub-expression. Okay. In the green, we have an OR, and this OR is going to apply to this sub-expression in this sub-expression. Okay, in that particular order. So, thinking recursively across all the different steps, if we can assume each sub-expression to be evaluated, we can evaluate the current logic operator as being equal to applying some left sub-expression and some right sub-expression across some common operator. Okay, so for example, we can look at this OR symbol here in particular. If this left-hand side is already parsed, everything I've underlined in green is already parsed. We just assume that it's parsed in a previous step. Similarly, and the right side is already parsed. We just assume we've already parsed it in some previous step. The result of parsing all expressions across the green line is equal to an OR operator applied across the left-hand side and the right-hand side. Okay. Similarly, in the blue, if we assume the left-hand side is parsed, if we assume the right-hand side is parsed, the result of parsing this whole sub-expression is an AND applied across this sub-expression already parsed and this sub-expression already parsed. Okay, so our recursive step then is just that, finding our operators and applying the operator across stuff that's already parsed. Okay. The third thing, we're going to think about order, and recursively we generally start at the biggest assumption we can make and work our way down to be more and more specific until we recurse out. For example, as we showed in green, the full expression is equal to an OR of the left-hand side and the right-hand side. Okay, that's the most generic, I guess, full expression that we can evaluate. So when we parse this, we want to be parsing this eventually last, but trying to find it first. Okay, if we can find this first, and then in some future steps evaluate this, by the time we recurse back to the start, this should be already evaluated, and our final expression will be completely solved. Okay, So our base case will be when we've tried to find some logic operator in the string we're attempted to parse, and we haven't found any. And in this case, we simply just have a symbol, and we can just return a symbol object. Okay, so if we have some sub expression that we're trying to evaluate, and we don't find any other logic operators inside, then we're just going to return a symbol. So that's our base case. And again, we're going to start by finding the lowest order of precedence, recurse in by evaluating the parsing of each sub-expression, recurse in until we find that base case, parse that base case, and use that in our outer expression. Okay. Just quickly before we start coding as well, the other requirement is that we have to remove all white spaces. Because we're going to be parsing every sub-expression of the full expression, we find that removing, trailing, and leading white space from every sub-expression that we're going to parse and or evaluate, that is going to result in removing all white space in the code. The easiest way to visualize why this is to place brackets around each sub-expression we're going to be parsing. Look at the left and right of each open and closed brackets, and then it's quite easy to see that this will remove all possible gaps, all possible white space within the code. Okay, so now let's see how we can visualize this recursion in code. Okay, so I have my parse function here. And using the information that we've got on the left, the base case, recursive step, and the order, we're going to start to look how this can be represented or implemented programmatically. Okay, so I'm going to start by commenting. So we explained before that we want to start by parsing all we want to start by parsing ORs first. Okay, we want to be getting an OR, finding an OR because it's the least important, and the result of the whole expression will be the result of ORing together all the sub-expressions that are linked by an OR. Okay, so say we had here OR D. Okay, this whole sub-expression would be equal to this green part or this green part or D. Okay, so first part, we're going to find all the ORs, where they are located. Okay, so if we're going to check something where they're located, we can use the string function contains. So if string contains or, then we're going to do something. Okay, we're going to look at parsing each sub-expression and returning that. Okay, if we don't have an OR in a particular expression, okay, or we've already parsed the ORs, and the sub-expression that we're passing to parse only has ands, nots, symbols, okay, the next thing we want to do is parse and applied to all sub-expressions. Okay, once we've got rid of the ands and we're evaluating the sub-expressions applied between the ands, we're only going to be left with negations and symbols. Okay, so we want to be parsing negation. Okay, applied to the sub-expression to the left of the negation symbol, sorry, to the right of, that's to the right of the negation symbol, because we're going to have a negation symbol and then everything to the right of the negation symbol is going to be negated. And then everything, sorry, a particular string that doesn't contain any ors, that doesn't contain any ands, and doesn't contain any negations must be itself a symbol. Okay, so if we've just got a symbol in the string and we know it's definitely going to be a symbol, we can return a new symbol object with the value of expression. Okay, remember this works because parse is going to be called recursively. Pardon me, we're not just applying this across the whole original expression, we're also applying this function to each individual sub-expression. So for example, this green part, the blue part, the red part. So we can very easily see how when we're applying it to the different sub-expressions, how we're going to go through these individual steps. Okay, so if we have an expression that contains a vertical line and or, remember that we said that we want to apply that or across the sub-expressions, the result rather, of parsing all the other sub-expressions connected by an or. Okay, so we want to pass this, and pass this, and then the return at the OR step is the result of ORing all those parsed sub-expressions together. To get those sub-expressions, we're going to use the split function. We're going to split on the vertical line, and the split function is going to return an array of all the elements with the symbol removed. I had a question in the practical today about why we have this double line here, and that is because the vertical line that is used here is not simply a delimiter by itself, but it's something called a regex, regular expression. A regex is, in essence, a short way of representing some particular strings, and in this particular syntax of regex, a vertical line has a special meaning, and the escape code, the escape character for regex is 2 slashes. So all we're meaning here is that we're going to find a vertical line and split on that. It's nothing more than that. So now that we've got the string representations of the different sub-expressions, we want to then parse all those sub-expressions. And we want to collate them in an array. And the reason we want to collate them in an array is because eventually we're going to return an OR of those parsed sub-expressions. Okay, so I'm going to create a logic array, and that's because logic is the type that has resulted from parsing a particular sub-expression or expression. And so we have an array of those results of parsing something. I'm going to call this sub-expressions, and that's not to be confused with parts, which is the string representation of those. So this is the original string. This array is eventually going to store the result of parsing each of these individual elements. So we have that equals a new logic. Its length is going to be the same length as this. And then we're going to use a for loop to populate the sub-expressions array. Each index in sub-expression is going to be populated with the result of parsing that particular sub-expression at the same index in parts. Once we've got the result of parsing all those sub-expressions, we can return an OR across all those sub-expressions that we've just parsed. Okay, so going back to our diagram over here on the left-hand side, the final step that we're going to be calling, I guess, the outermost recursive step, is that everything should be an OR with the contents of an OR being applied across that sub-expression parsed, the C parsed, and D parsed. Okay. Similarly, if the sub-expression contains an ampersand, we're going to split at the ampersand. We're going to create another sub-expressions array. We're going to parse all those, and then we're going to return an AND across all those sub-expressions. Negation is slightly different. Because it's only applied to one particular thing, we can parse it slightly differently. We still have the if statement to check if there's an negation symbol there. In this case, the tilde. But the negation, because it's always going to be on the left-hand side and it's applied to everything on the right-hand side, the result of applying a negation is negate across everything where the negation isn't. Everything in the sub-expression where the negation isn't. For example, over here on the left-hand side, we have negation of A. The negation is applied to everything, that whole sub-expression that we parsed, that whole blue line, without the negation in it. So we can return a new negate object across the result of parsing the sub-expression without the first element. Okay, substring from an index I is the beginning index, remembering that we're indexing from 0. So if we took negate A as our sub-expression that we're going to be parsing into the function, it doesn't have an OR in it, it doesn't have an AND in it, it does have a NOT in it. So we're going to return a negate of the parse of this whole blue part, starting from the 1th index. So we're actually going to be negation of the parsing of A. So that's negation of symbol A. And that's the whole function. The only additional helper function that we provide here is parse expressions. That's simply because we can apply this looping. We apply this multiple times, and it's in exactly the same format. As a quick way to, I guess, extrapolate this kind of functionality, if you're an IntelliJ, you highlight some repeated code, you right-click, we can refactor and extract this method, and we can say logic array subexpressions equals a function call. I'm going to call this as here. What does it do? It parses subexpressions. Okay, because what it does is it loops through all the parts. Maybe we'll call it parse parts. We're gonna feed it a part, and it's gonna return a bunch of logic expressions. We can copy that line to here, and again, all this does is just takes in this parts and applies parse to all elements in parts. Kind of like a mapping, if you've done mapping before. And that's all of the parse function. To have a look at how this actually works, we're going to need to apply some toString functions. Hopefully you should be as familiar with toString functions by now. I'm going to go away and apply them quickly and then jump back, and I'll show that this definitely works. And now I'm back in 0.1 of a second after pausing that video, and I've just applied the toString methods that are supplied within the answers here. Hopefully you got to that in your practical. If you're unsure about those toString methods, feel free to have a chat to your demonstrators in your relevant practicals. But all it does is it's going to represent those particular sub-expressions as such. Logic symbols, and fingers crossed. So again, we have a logic. We want to be parsing a string, and the result of parsing a string should be putting this string in some meaningful objects. We're not evaluating it yet. We just want to put them in some objects in a meaningful way. And those meaningful objects are going to be of type logic. When we want to then display that to a console, because we've just got an object at this stage, we then need to define the toString methods, etc. And hence, we then need to print out the expression that we've just parsed with those relevant toString methods. Let's make this static and this static too. And hopefully, probably helps if I put it in the right place. Cool. And let's see what we get here. Live coding at its finest. We need some elevator music. Note to self, insert elevator music here. Awesome. Ah, live coding is its finest, as I said. So we can see that the white space hasn't been removed. We forgot to add the trimming of white space of all the sub-expressions. So remembering that because the parse function is called to each sub-expression, parse is called to each sub-expression that we've located in there, trimming all the sub-expressions will result in trimming all white space from the whole expression. So we can just call this, and now let's see if we get something nice. Beautiful. Okay, so we have symbol A, that's applied across an OR, and that OR is to the negation of a symbol B and the negation of a symbol C. So far we've reached there. Or the symbol D, or the symbol Z. That is all contained within the outer expression. Hopefully that has simplified things a bit. I might do a quick tree diagram of the function calls that will be created, so we can trace this and watch how the function calls work. So we're going to call parse. Let's work with the previous example at the top here. So I'm gonna start with not A and B or C or D. We're gonna parse this is going to be the expression. This is going to be, I'm going to call this a value rather than a return. Parse1 is going to parse the whole thing. We're not going to return anything yet. We're going to call a parse on this part, parse on this part, parse on this part. So I'm going to call those parse2, parse3, and parse4. Parse2 is going to parse this, parse3, and parse4. The result of attempting to parse that is going to be a new parse call of that ended to that. Parse5 is going to be not A. Let's do insert a row here. This is going to end of the array parse call to not A and parse call to B. Six to B. Parse C is just going to be a base case, which simply looks back here, returns a new symbol expression. So we've got no calls, we're going to return symbol C. This is then going to recurse up to this location. We're going to start with that at this element here. D is not going to have any parse calls. Same there. Not A is going to negate A. B is simply going to be simple B, and that's going to be used here. Or of something and something. Symbol D was declared here, sorry. And cross something and symbol B. We haven't evaluated A yet. We need to make an A call. A call. That's not a parse call. Symbol A. That's going to return up here to be the negate of originally something, which is going to be replaced by this value here. Then we evaluated this expression as this, so that gets replaced up here. And then we've evaluated this expression up here, so we can replace this with this. Hence we have an OR applied to 1, 2, 3, 4 elements. Should be 3 elements, sorry. 1, 2, 3 elements. 1, 2. This is a different problem. But yes, very similar. I've just reformatted this table in a tree structure. We can see that each element here represents a call to the parse function on a particular sub-expression. We start with the whole expression. We're going to parse each sub-expression. So those are all the sub-expression parse calls. When we reach here, we attempt to parse this sub-expression. We split at the end and parse each sub-expression in there. Similarly here, we're going to parse the sub-expression, everything to the right of the not symbol. Once we reach just a symbol, that is no logic operators within a particular sub-expression, we can recurse back by returning a symbol, as we do here, or here for this particular example. And when we recurse up, we simply apply the operator at that particular position to the result of the sub-expression that we've parsed. For example, here we have the not operator applied to the result of parsing a symbol. So the not applied to the symbol A. Similarly up here, we've parsed B, we've parsed not A. The result of this is going to be the result of applying AND to the result of this parse and the result of this parse, which can be then used in the final expression evaluation. Hopefully that has been useful. Best of luck to everyone with your assignments. Keep the ed discussion questions coming. We do love watching and seeing what you guys don't quite understand. Do keep coming to the practicals and asking excellent questions. I've had some excellent questions in the practicals so far that have been really well informed and really insightful. So please do keep asking questions, keep bugging your tutors or demonstrators, and I look forward to seeing you soon.